Hi everyone, and welcome to part 2 of chapter 6. In this part, we're looking at integrals of exponential and logarithmic functions. So the first thing we're going to look at is the integral of an exponential function. And when we have the integral of an exponential function, we use this formula here. So you copy the exponential function to the top, and it's divided by the natural log of the base. Don't forget the plus c if you're doing an indefinite integral. If you're doing a definite integral, you don't need the plus c. Now, I did write down the derivative formula. Notice these formulas are very similar. The derivative, you have a to the x times the natural log of the base. Here you have a to the x divided by the natural log of the base. They're very, very similar formulas. So that helps me remember them, to remember that the derivative is where you multiply and the integral is where you divide. And it kind of reminds me a little bit of the power rule, because in the power rule, you're multiplying by the power. In the integral form, you're dividing by that power. So that helps me remember it, okay? So let's do an example about that, and then we'll look at the natural exponential function. Our first example is this. It says, find the integral from 0 to 5 of 2 to the x dx. So notice this is an exponential function. There's nothing special happening to it, so I don't need to use substitution or anything like that. All I need to do is apply my formula. So the formula says, copy the function to the top, so 2 to the x, and then divide by the natural log of the base. Okay, now this is a definite integral, so I have to evaluate it from 5 to 0. So what this turns into is 2 to the 5th power over the natural log of 2 minus 2 to the 0 power, or 1, divided by the natural log of 2. 2 to the 5th power is 32. So when I subtract these, now notice they have common denominators, so I am allowed to subtract. I get 31 over the natural log of 2. And that is my answer. Okay, the next thing we're talking about is the natural exponential function. That's the e to the x function. And remember, when we did the derivatives, the derivative of e to the x is just e to the x. The same thing is true with the integral. The integral of e to the x is just e to the x. Because remember, these are opposite operations. So if nothing changed here, then nothing's going to change here. Okay, and don't forget to add the plus c on the end if you're doing an indefinite integral. So let's take a look at an example question here. In my example question, I have the integral of x squared times e to the x cubed dx. Now, one thing to be careful about is that we don't actually have a product rule for dealing with integrals. So we're going to try dealing with this through substitution and see if that helps. So I notice my inside function is going to be this x cubed here. So I'm going to let u equal x cubed. The derivative of that is 3x squared dx. Now notice almost all of that shows up in my original integral, except for that 3. So when I'm looking for things to replace, I notice that I have this x squared here, which matches. And I notice that I have the dx here, which matches. So I just need to get this 3 to the other side, and then I can substitute. To do that, I'm just going to divide by 3 on both sides. So I just get 1/3 du. Now I can do my replacement. So this x squared and dx is going to be replaced with the 1/3 du. So I have 1/3 and a du. This e to the x is going to turn into e to the u. And I can't forget to write my integral in there. Now I can apply my natural exponential function, because this is just a plain e to a variable. So this is just going to be 1/3 e to the u. Now, this is indefinite, so I should put a plus c at the end. And the one thing to be careful about with these is because it's indefinite, we have to make sure to replace the u with what it was at the beginning. So this is just going to be x cubed here. And that's the answer. Okay, it's very easy to forget to replace that u because when we do definite integrals with these, we don't always do that. So let's see another example. Okay. In this one, again, I'm going back to this natural exponential function. They want us to find the area under the curve of y equals e to the negative 3x from 0 to 1. Now, area under the curve is referring to an integral. So I need to do the integral from 0 to 1 of e to the negative 3x dx. Okay? Now, again, I have something more complicated here than just a variable, so I need to use substitution. I'm going to make u equal negative 3x. So du equals negative 3 dx. Now, looking for my replacement, I notice that the dx can be replaced, but that negative 3 doesn't actually show up. So I need to divide on both sides of this by negative 3. So this becomes negative 1/3, and that's going to disappear. Now I can replace. So I have the integral of e to the u du, and I can't forget my negative 1/3. And now for these limits, it's up to you if you want to replace them with new limits based on our u value, or if you want to keep them and then later on go back to x and then evaluate. Personally, I like to replace them because I always forget to go back to x's. So all I'm going to do is 0 and put it in here. So 0 times negative 3 is still 0. And then put in the 1. 1 times negative 3 is negative 3. Okay? Now, notice with integrals, it's customary to have the higher number on top and the lower number on the bottom, but it doesn't really matter. So I'm going to leave it like this. If I wanted to switch them, all I would need to do is switch the order and change the sign in front. So it's up to you how you want to do it. I'm just going to leave it like this and deal with it later. Now I can do my integral. This just stays as e to the u, and it's negative 1/3, and it's evaluated from 0 to negative 3. I'll put in my negative 3. So e to the negative 3 power, so it's negative 1/3 times e to the negative 3 power minus e to the 0 power is just 1. Okay, now I can simplify this part. E to the negative 3 power is just going to be 1 over e to the 3rd if I wanted to. So I can write this as negative 1/3 times 1 over e to the 3rd minus 1. So that is our answer for this one. If you had switched those limits, it would look a little different. It would be 1/3 times 1 minus 1 over e to the 3rd. So you could have gotten that if you had switched the order of those limits. Okay, so let's take a look at example 4 up there. Example 4 actually has to do with this, the natural logarithmic function. Okay, so if I have the integral of a natural log, you're going to use this formula. It's x times the natural log minus x plus c. Now this doesn't appear to be involved with our derivative formula, but notice that derivative formula was this one. The derivative of a natural log of x equals 1 over x. So if I do the integral of 1 over x, I'm going to get the natural log of x. Okay, another formula that comes up with natural logs is the integral of tangent x. Notice we didn't actually have a function or a formula for this earlier when we did trig functions, but now we do. It's the natural log of the absolute value of secant x plus the constant. So we're going to be dealing with these three formulas in our other examples. So looking at example 4, we had the integral of x over x squared plus 1 dx. Now remember, we don't actually have a quotient rule to do this integral, so we can't simplify it, but we can try substitution in this. So I'm going to let u equal x squared plus 1, because that's the more complicated one here. And I'll find that du equals 2x dx. Okay, now notice if I'm looking for substitution, I see that the dx's can be replaced with each other. I see the x, just the x, can be replaced up here. But that 2 doesn't have anything it can be replaced. So I have to divide by 2 on both sides. And then I'm ready. So now my integral is going to be 1/2 times the integral. Now this gets replaced with u. This x and the dx are going to be replaced. So it's 1 over u, okay, du. Now this is the formula right down here, which kind of went off my board a little. There it is. It's the integral of 1 over x is the natural log of the value. So this is going to be 1/2 times the natural log of my u. And the u was x squared plus 1. And don't forget the plus c at the end. Now, I don't actually need these absolute value symbols because x squared plus 1 is always going to be positive. Because whenever you square, you get a positive value. Then you add 1 to it, so it's still going to be positive. So those absolute value symbols are extra. I can simply just use parentheses to show that they're all in the natural log. And that's my answer for that one. We're on to our last example of the lesson. I know this video is getting a little long, but one more example. We can do it. Okay. So example 5, we're given this. Now again, this is a complicated thing that can't be simplified. So I'm going to use substitution again. And it's a little hard to figure out what I should substitute. So if you pick the wrong thing first, just try it. And if it doesn't work, pick the other part. So I'm going to pick the natural log x first. So I'm going to let u equal the natural log of x. So I know the derivative is going to be 1 over x dx. Okay? So notice that this is actually what is in my function. I have the dx, which matches, and the 1 over x, this part here, is actually right here. Okay? So those can both be replaced, so I just have a du that's going to go in for them. And the natural log of x is going to turn into a u. So I have the integral of u du. Now, I can take this and put them in. The natural log of 1 turns out to be 0. And the natural log of e turns out to be 1. Okay? So now everything's set up. I can do my definite integral and see what happens. So remember, when we're doing a definite integral of a plane number like this, I go up by 1 on the power, so it's u squared. Then I divide by that power. And it's evaluated from 0 to 1. So putting in the 1, 1 squared is 1, so it's 1 times 1/2 is just 1/2. 0 squared is 0, so 1/2 times 0 is just 0. So it's 1/2 minus 0, or just 1/2. And we're done. Okay, that's it for this lesson. Let me know if you have any questions.